Thank you. Okay, I'm sorry for this bit of very strange title, right? It's the Ceresa cycle, Gross-Schoen cycle. So I know the conference always talks something extremely general, but I guarantee that the cycles are invariants, general invariant algebraic curves. We don't have many invariants, right? So we see some omega square fault in the heights. This is one more invariance. This invariant has an advantage than other two invariants, omega square fault in the heights, because it's related both automorphic word and diphonic word. So that's one thing I found is very fascinating. So I mean, about 20 years ago, I always dreamed you can prove ABC using Lagrange program. And I still dream. So anyway, I will start with since it's about the curves, right? I can change another title called arithmetic of curves, but that's a bit too universal. So we start with the Riemann surface. About 200 years ago, you probably want to study from Riemann, Jacobi, Abel. You're going to study this Riemann surface. Originally, it's algebraic curve, then become a Peirce integral. Riemann eventually come back to curve again. So you have a Abel-Jacobi map. You get a torus there, and then this is the curve C. Then you go to you pick up integral. You get the H1 of XR, whatever. So you get an integral there. The Jacobian C. So you start with the point P here, P0, P there. You get a P0, you get a P there. You can pass integral, then integrate. Then there's a P goes to integration of P0, P omega 1, P omega G. Yeah, this is the C to the G modular lattice. This is Abel-Jacobi map. The remarkable theorem is that you can do this about the divisor. So this basically do integration. You get to pick 0 of C map to isomorphic Jacobian of C. This is the remarkable theorem. From this integration, it's not quite clearly you get this theorem right away. Then 100 years later, then you start with the Poincare trying to make this thing completely arithmetic. And the way, okay, I forget about it. So if C is, for example, before that, at least Riemann know that this Jacobian of C is in fact is a projective variety. This is at least by Riemann. 100 years later, then is Poincare initial study arithmetic of curve. The way, if you maybe 30 years later, 20 or 30 years later, completely algebraize all the theory. Algebraize the theory. So essentially, he can prove that if C is defined of a number field K, this implies that the J Jacobian C is also defined. If this is defined, it is also defined by K. If K is a number field. So not only that, you can embed this into the Pn to the K, right? You get this in. Then few maybe 10 years later, his proof of Mordell-Weil theorem. He introduced implicitly so-called the height theory and the dynamic system. This is by Northcutt. 1940 something, 49. I forget which year it is. 42, they introduced the height theory. It's a remarkable theory. I mean, it is proven model where you already implicitly use heights, but it is not cut formalize the process of the of a way. And Northcott actually has a very interesting story and the thing. He originally wanted to come to Princeton to study Banner space with Van Neumann, but Van Neumann somehow doesn't want to work on this stuff anymore. So he started with Emil Artin. Emil Artin has a workshop, so study Wei's work. Then from that one, he wanted to apply this high theory for a dynamic system for PN to PN. Then he wrote the formal similar high theory. Then a few years later, Wei wrote another paper. The title is called Arithmetic Algebraic Varieties. But the whole paper is talking about the high theory. So arithmetic really means some way to count, right? So you need to have something to count the points. More than that, Wei done a lot of work. So this is basically by Wei. Not only he formalized Jacobian, he also introduced starting the theory, the initial theory. He initiated the study of algebraic cycles. And the intermediate Jacobian. So the idea will be, you think about Jacobi theory, but Picard zero, you should have something like a Chow group. If you have a variety X, you have a Chow group of X. So this is a Chow group. Say I, whatever. The Chow group could have a cohomology map, class map. So then you take a kernel. So the homological trivial cycles. The homological trivial cycles, you want to create something can be used to study this thing. And the idea is pretty similar. Instead of H1, you're going to study H with a 2i. I always forget I is upstairs, downstairs, you know. 2i minus 1 of x, a real number, H2i minus 1 x of z, right? Plus. I don't know, I get confused.
Plus fi.
Plus fi.
Plus fi.
Plus fi. The quotient.
In the denominator, you have to model out the piece of the filtration.
Yes.
No, but fi of this one.
No, it's R. It's R.
The real number.
It's R.
You put R.
Is that fine?
Yeah.
No.
Okay, so this is an Abel-Jacobian map. And he put the complex structure there. When Griffiths was in his lecture, they found that this is not the right one. Then Griffiths changed one. The Griffiths, there's a modification by Griffiths, put a different one. So in modern world, then you twist this guy by, yeah, you get the two, you take their, whatever. I'm not going to talk about Hodge theory. So you're going to have it's more like, you know, the V. If you twist this guy by I there, right, you get the V of C, or V of Z, then F0, V of C. So, but this Abel-Jacobian map, this is not algebraic anymore. Not only that, this is not isomorphic, but this is not isomorphic. So you have some problem like that, right? So you will not going to get the same theory as in the Abel-Jacobi Wei's original theory. You have some problem there. Nevertheless, in 1980s, Bellinson and Bloch introduce the heights for these cycles, but it's introduced is conditionally. It's a condition. And then, of course, it then propose the generalization of the BSD conjecture. So suddenly become quite important subjects. I mean, that one, of course, in 1960s, then we have this remarkable conjecture related to the model wave group to the special value of error functions. Okay, so that's a very general theory. Now I need to have some physical work. Okay, I can use the two first. So it's 90, like 40 years ago, 83, Ceresa, in his PhD thesis, I think it's in Utah, and his advisor claims he's a very famous algebraician. He introduced a very remarkable theorem. He studied the cycles, and the same picture there, you have C embedded into the Jacobian. So you get there. You got a C here. Then you have a C minus. It's a minus x in C. You get another C. Of course, this guy is homology trivial, the C minus. C is a homology trivial equivalent. Homology equivalent. So I mean that you can have a real manifold. Right, you have a real manifold somewhere. You have this Jacobian X. You have some real manifold M inside. The boundary equals C minus C minus. Okay, you have a boundary like that, and he proved this theorem. He proved the theorem that generically C minus C minus is not homology trivial. It's not algebraically trivial. It's not algebraically trivial. Generic C. This set is published in the Annals, only 6 pages. The proof is remarkable. It's very similar to Urbanic's the first theorem. He actually do the reduction to the boundary to study general C, then move to the boundary. So when the Jacobian of C, he moved the boundary isomorphic to some abelian variety, derive some elliptic curve, where he done precise calculation with periods. That shows non-zero. So it's by induction.
So here generic is outside a countable union or a finite union of some variety?
Generic.
Generic is the generic point.
No, it's a generic in the complex topology. So it's high transcendence, maximal transcendence.
I think you prove very generously.
Very generously, yeah. Not in theoretic sense. So this is his proof. Later on, I will talk this again in this case. How the degenerate, okay. I mean, what is it doing is that, okay, sorry, it's not this. He degenerated the case is a curve, this is G minus 1, this is 1. He degenerated everything to the boundary. That's whatever his proof. In 1992 to 1995, the Gross His two papers, okay, Gross, one's Kudler, one's Schoen, and this is 92, this is 95, but the paper 95 relies on paper 92. I don't know how can he publish a paper before he actually done this. And this thing he really unconditionally defined the heights. Okay, maybe I write slightly more. He gave a different version. He didn't say precisely. He defined, so introduced so-called Gross-Schoen cycle. So first thing is introduce cycles. This is very similar to the cycle, but the define of the triple products of curve. So you have a curve C there. You have a 3C. You have x, y, z. You have to take the coordinates. Then this is the points. You start with the P0 in the very beginning. Then inside C3, you can embed in C in 6 ways. Either by 3 axes, right? Or by 3 partial diagonal. Oh, that's the main diagonal. Okay, 7 ways. You have 7 ways. Right? You have 7 ways to embed and sit inside. Right? You have 7 ways embedding. So then, okay, you take an alternative sum. You get a Gross-Schoen cycle. You take the main diagonal minus 1, 2, minus 1, 3, minus 2, 3, then plus delta 1 plus delta 2 plus delta 3. So you make some alternative sum, then it becomes homology trivial. And okay, so this is very nice. And then the Bellinson. This is first thing, the proof. The Bellinson block heights are well defined. And the most important thing, they propose a generalization of Gross-Zhang formula. For triple product L series, so the idea will be fine. The idea with the following: if you take C to the modular curve, or Shimura curve, for example, Shimura curve. Then you have the delta G of S inside the Chow group of 2 C cross C3. And this guy has a high cooperative action. 3 copies of high cooperators. Okay. So suppose you have 3 module form FGH, 3 custom forms, or where 2, then you can use high cooperators to cut the space according to the coefficients of the 3 forms. So you're going to get data FGH. So this is still a form. The inside CH2C3 over some coefficients. So over C, for example. Then they made the conjecture that FGH, this is the Bellinson plus the heights, is equal to something like derivative of at the center of the triple product L series. Okay, the L series, something like that. Some constancy like this stuff. Yes, so about 20 years ago, so when Sheng and we at Columbia, we're trying to do something. So we have two YZZ programs. One's finished in 15 years ago. One's still not finished yet. So, so that's 20 years ago, I started thinking of this problem with my students. They're still first year, I forget it, maybe first or second year. So 20 years ago. Okay, so I done one thing. So I think these cycles give you a seed. This Gross-Schoen cycles. Of course, it is if we give you a curve, you get a number, right? I mean, it's a number attached to a curve. So it's a self. I needed to explain what this number is. Second thing is related to error function. For error function, of course, we have many things to talk about. For example, GRH, a lot of things. So I started to study the two different words. One is the Diophantine word. One is automorphic word. And it ended up, both of them are quite interesting. So I can talk this in a little bit. Later on, we'll talk this word. Sorry, I never use this stuff anymore. Okay, let me try to use this stuff.
Wait, what number were you referring to? You said you have a cycle, your delta GS, and then you
for a curve. So you can get a number, right? Height is a number. Yeah, so this is a number. I need to explain what this number is. It's a new number attached to every curve, right? So it's not a, so it's very special, but not that special. Later on, I will explain the general recipe to construct more algebraic cycles. I know in the algebraic cycles, of course, general theory is extremely hard. Another hard thing is we don't really know how to construct the cycles, which is fairly general, but still handleable, right? If I mean, too general, we're not going to handleable. Too special is not going to be useful. The first theorem in Diophantine word, so I proved one theorem in 2020 with help from my students. Like we have been allowed is C, if C is over K is a curve over number field. Then I choose a best point. Okay, I choose a P0, a best point. So because this Gross-Schoen cycle depends on the best point you choose. So you have the delta GS of the balancing block Hadaparian has an equality with something appeared in the previous lecture. It's omega square. Yeah, this is admissible. Duality in sheaf plus 6 G minus 1. And it's already in the Sheng user lecture of the P0 minus omega 2G minus 2. The narrative height. Then plus minus summation phi, Sheng is rather big phi. Log n of v. So we prove this inequality. And Well, in this equality, then you see this invariance is nothing really new invariance. It's old invariance, right? It's nothing really new, expressed by this guy, this guy. This is a bit of mystery, right? Is the invariance, and maybe Emmanuel and I maybe were trying to look when we were young. So in fact, this Archimedean one has connection with the string theory. Later on, people realize that, right? So with the string theory, and the Archimedean place, non-Archimedean place is completely new. And eventually, and I think in De Young and Robert Williams, they use this thing to give a new proof of the Bogomolov conjecture with effective bond. So omega square bigger than 0. This is by Emmanuel. Then they, but somehow, if we believe that time, if we believe, I mean, if we assume the Huygens theorem, conjecture theorem. So there's a conjecture by Huygens index. What let me call it? Called Riemann Huygens conjecture by Gillet-Soulé. I really mean that the data, this guy, should be non-negative. If you believe this is non-negative, then of course, then you get a lower bound of this guy. This time I knew that, but anyway, a few years later, De Young, Williams, they bypass this conjecture, still give a proof. So this gives a proof omega square greater than 2g minus 2 over 2g plus 1 summation by xv. And this thing can be easily calculated.
But half of it.
What?
Sorry. It's not what we did with.
No, I said this is a conjecture implied this. You guys, what do you do half of this? They prove something slightly smaller number of same sum. I don't remember. You can see in Shin's lecture, he has a number like this. What's the number?
Just half of this.
What?
V minus 1 over just half of this.
Just half of this? Oh. Okay. So g minus 1 of 2g plus 1. Yeah. This will be this relies on the Huygens conjecture. We still have no idea. So this relies on the question about the positivity of this number. Anyway, this inequality tell you two things. The lower bound of this number, positivity of this number, is related to small points. But if you're lucky to get upper bound, even better, you get ABC conjecture, because upper bound will related to the upper bound omega squared. That's something we're looking for. Have much bigger consequence. So study these heights of the Gross-Schoen cycle. So the remarkable, I'm just trying to say. So anyway, so give you two things. That is the upper bound. Okay, so there's the positivity of this Gross-Schoen cycle is related to the Bogomolov conjecture. And their upper bound, a nice upper bound, related to the effective model. So this means small points, right? This means the bigger points. So it's kind of a very fascinating. Same for me, it's kind of a mystery. Okay, so that's good. So we have two parts. From my work itself, another consequence, we have a Northcott. Now we talk about Northcott property. So the positivity we don't know, but from this work, it's pretty clear if S is inside Mg. So if this is a proper, the proper subvariety, then Northcott hold. Then you can prove that if this is a proper, then we can show that we have Northcott property for proper variety. Then you can show that the X inside X Q bar, the height of X less than H, degree of X less than D. This one is a finite for any H and D. Just from this equality, you will get the same. But you need to require that S is a proper subvariety.
What is H?
H is high.
Which height?
Yeah, okay. Yes. Of X. Right, you will get this inequality. And but the properness is very hard to remove. Because we have no idea what happened near the boundary. Because the minor inequality is, you have to assume the variety is smooth. We don't know how to define the Gross-Schoen cycle for singular variety. And this thing is changed very luckily in the last year. In my work with Zhang, we prove this Northcott property.
So how does it follow? So if you have a proper subvariety, then
you get a smooth family of curves. Then this associated line bundle becomes a divisible pairing. Omega bar square will be ample line bundle unmerged on this variety. So this follow from Fulton's Northcott. So you replace this guy by Fulton's heights. Yeah, I mean the upper one basically say this GS is this is the height associated Deligne pairing of X, right? But this guy is ample bundle.
okay.
Yeah. Okay. Yeah. So but that because you're proper. It's not proper. You could go to the boundary. Then you have something happen.
So the phi of equal.
Phi will be bounded functions.
It's like minus the distance to the boundary.
Yes, more like that. Shane's lecture already explained how phi grows to the boundary. Okay. So this is the situation in 2010. So it took us almost 15 years to realize that just extend the theorem, drop the condition of properness. So the theorem we proved last year with the Zhang Gao is that we drop this condition. So we drop the properness of S. So how do I drop it? If you drop it, it would not be true. So they proved by the following way. So they exist for G, of course. Okay. One thing is very important. G is always greater than 3. G equals 2. Okay, that I'm sorry. G equals 2 is, let me see what happened in G equals 2. That formula still works. Yeah, when G equals 2, the Gross-Schoen cycle vanishes. The reason the Gross-Schoen cycle will become a divisor is a divisor in the Jacobian. For divisor Jacobian, we know minus C and C are translation by torsion points, by Weierstrass points. So we're not going to get anything. So, okay, I just said that's delta GS equals 0 is torsion if G equals 2. So the axis are open subsets, non-empty. U inside MG, defined over Q, and U is not empty, such that so NX inside U of Q bar. Oh, I have. Oh, yeah. I'm sorry. Be very careful. I'm stupid. Is it fine? Do you know what I'm thinking? I said hyperelliptic curve is a problem. Hyperelliptic are fine varieties. There's no problem. Yeah. So the degree of x less than d, gs of delta of gs of x, gs of x less than c less than h is finite for any d and h. So that's the and of course now what's left I could be a reason why I cannot prove it 2010 because we realized so much of the modern theory. The proof have a few ingredients, basically 3 ingredients. The proof. So I talk about the ingredients of proof.
Sorry, Shouwu, before you go on, is the complement of U understood?
U is explicit. Explicit some way in Hodge theory. but it's remaining a big problem. We really don't know how to construct U explicitly, algebraically. I mean, Hodge theory means that as a transcendental variety, we know what this is. As an algebraic open subset, we have no idea. So we show this algebraic defined over Q by a very strange method. But it is a big problem. I think this theorem is completely useless unless we know what the U is. Agree?
Yeah. But you know it contains all the properly solved values.
Right. I mean,
can you describe it for special G, perhaps?
Yeah, I mean, for example, G equals 3, we have no idea what this is. Yeah, this is a question challenge I ask Richard Ham for every time I met him, I say, what the U is, what the U is. He actually gave me a conjecture. The conjecture is very nice. Okay, if you want a U, okay, I'll make a conjecture for G equals 3. Okay, so G equals 3. This is probably, you don't want to listen to the rest of the lecture trying to calculate what the U is. Okay, so the G equals 3, the conjecture is the following. So the MG, of course, right, it's just the forget of hyperelliptic curve, non-hyperelliptic curve. It's nothing, it's just the quintical curve, right? The curves inside P2 of degree equals 4. So it's defined by one equation of the C3, right? We have defined by one equation, a 3 variable degree 4, right? F equals 0. And but a modular space, a tangent space of modular space, is a symmetric square of C, right? So each F induce a quadratic form on tangent space, right? up to scaling. So then U, the conjecture. So I don't know, it's my conjecture, it's a Richard Henry. I mean, maybe I propose a question, maybe I call a question. It's a conjecture because we have zero evidence. Question. Is U the non-degenerate? Is U the non-degenerate locus of this quadratic form? Let's give them like a QF. Okay, right? Because for G equals 3, then you really get you have a defined equation. Defined equation will give you a quadratic form, and space you can write precisely. You actually calculate determinant. So determinant have a non-vanishing. So basically, that's whatever you want to do.
Can you show an inclusion at least?
What?
Can you show an inclusion at least that U should not contain that?
Yes, inclusion is no. Yeah, but we don't know if this is the right one. If this is true, it's fantastic because we know, okay, I mean, we know exactly which points will be non-trivial. For example, inside this space, every transcendental point is non-torsion, right? That's already very, very remarkable. It's much stronger than Ceresa proved. Forget, yeah, in my 2010 paper, actually, I make a connection between Gross-Schoen cycle and Ceresa cycle. I think morally people know they have related to each other. In my paper, I write precisely the heights of one cycle vanish if and only if heights of other cycle vanish. So that's basically the Ceresa cycle, the Gross-Schoen cycle, basically you study either one of them.
So when you say Ceresa, that's the C minus,
yeah.
C minus? Right?
Yes.
Okay.
Okay, so now I talk about ingredient of proof. The first thing is height inequality. So this already appeared in the work of Dimitrov, Ziangao, and Habeck. And it is further generalized by Xinyi and I. Okay. So we use this thing in there called identical line bound quasi-projective variety, but it really initiated with Dimitrov, Habeck. The whole point will be the following. So this guy, first of all, we have a line bound. It's Gross-Schoen cycle, as I said, GS. This actually is the height of something, some line bound of L of X. So this line bound actually can be written down precisely in a Deligne pairing and a dynamic system too. You know, this guy is Deligne pairing of 3 pieces. You have, okay, let me write this bundle there. Let me see. The Poincare bundle. Restricted on C square. This is Deligne pairing. So I explain what does it mean. So if you have a curve, then embedding to the Jacobian. I use a canonical embedding. So x goes to 2g minus 2 x minus omega 2g minus 2. Then you take a 2 copy of that. You take a 2 copy there. But this guy you have a Poincare bundle. Let me write this in. Okay, the write this is F. You pull back this bundle, you get this bundle there. Here you have modular space. Okay, and so then of course this is the surface of the modular space. You take a fiber intersection 3 times. That's the one you get, right? You get a really precise bundle you can construct. And the Shouwu has a different construction using omega square, but this one is simpler, but it's equivalent. So you get this bundle, and the whole point will be so the theorem of height and quality said that you need to show that this guy is this guy is idyllic line bound. I will not explain. So this bundle is on idyllic bound on Mg. Idyllic means that you need to compactify Mg by many different ways, like Riemann Zariski space. Take all projective limit. This bundle will be limits of some bundles, and what we do is the height equality say if L is big, then what happens? The height is defined by L of x will be greater than epsilon height on a modular space. Some height modular space. For example, we like Ford's heights. For example, minus c. Something like that happen. Okay. On open subvariety of Mg, this is going to happen. But this, of course, implies a notch cut, right? So this is the first ingredient, but of course, we have to show this guy is big. L is big. You don't need a body. Yeah? I mean, L tilde, L tilde is, I forget it, but generic fiber. Generic fiber. No, sorry. Yeah, I don't want to explain. You read my book. This is the notion of this stuff. Yeah, it's going to be published. So this is the first ingredient. The second ingredient is quite important. It's a volume formula. So the bigness means that something is big. The bigness, forget to say, bigness means that, okay, I forget about definition. For a variety, projective variety, bigness means that your variety has a lot of sections. So let me write it down. So if X is a projective, there's a line bundle, there's a projective, we have a notion called a volume. So this is essentially, you compute the sections, Rn, you count the dimension, right? Then you divide by n to the d factorial. You take a limit, n goes to infinity. This actually does exist. This is called a volume. This is a purely algebraic notion. The volume formula say volume is really volume. Okay, so what does that mean? The volume of the L is equal to integration of C1 of L, 3g minus 3 of mg of C. And this is not clear at all. It's very, this side is purely algebraic. This side is purely transcendental, right? So this is basically the volume formula. To prove this formula actually quite involved. At the very beginning, I thought it was easy. So actually, we have to use intensively that the MAI is what? It's a more theory.
I'm sorry, L is defined by X.
What?
L is defined over X. X was a curve or what?
Oh yeah, I'm sorry. Yeah, this is X. Yeah, this is the definition for our L. Sorry.
Okay.
So this is the theorem for our L.
But L is defined over X, so where
This L. Let's write this M. Okay. This definition. I just defined it. I just defined what the volume is, algebraic volume. Algebraic volume is just counting the dimension.
And now you take L to be?
To be the L.
Okay,
Yeah.
Thank you very much.
Yeah.
Thank you.
So I want to say this algebraic volume is really the analytical volume. Right.
Is it true for any big line bundle on a project? No.
What?
So if you have a big...
Oh yeah, L is big. If and only if, there's M is big. Let me write M here. M is big if and only if volume M bigger than 0. So this is the definition.
Okay. And the equality is
bigger.
What?
The equality of the volume is equal to like this kind of Riemann row.
Yes, volume we call this then.
No, but this Riemann...
This is the definition.
No, but the equality...
This is the theorem.
For every big line bundle? No.
Just for this line bundle.
For this particular...
Yeah. I mean, if you assume a line, if you already know L is a NAF, then this actually is a consequence of my work with the Xinyi. But we don't know that. We don't know that that bundle is a NAF. So there's a whole difficulty.
In the construction, you need to minus something.
Constraint minus?
Yeah, if you pull back and then you minus the partial pullbacks.
No, what do you mean partial pullback? So I get a bundle downstairs.
Yeah, but it's not the F star P, it's the F star P. The P
So C squared, yeah.
It's a minus something.
Okay, I don't know.
Okay.
Well, anyway, I get some Hermitian line bundle. The Hermitian line bundle already quite interesting. It's a new and the modular space. So we get the Hermitian line bundle. We compute one form. And this one form is always non-negative. It's the same positive.
I'm sorry, I'm still confused. So the definition of the volume is for proper variety or projective variety. Mg is not.
Yeah, so then you have read my book, how to define volume of quasi-projective variety.
No time now. Maybe you can say a word how to define the volume on
Yeah,
a line
so,
bundle which is not on the proper variety.
So, okay, so identical line bundle means the following. You get Mg, right? Then you take a bar. Then you have another Mg bar of many as n there. This n is not the modular space. And you get a sequence of a projection. There's a like, what do you call the Riemann-Zariski space, Zariski-Riemann space. So then you get a bunch of line bundles here over the projective variety. Then you compute a volume, what is the Ln there. Then you take a limit. Then you will get a volume of that one. So you need to have a...
So here it's over Mg bar, or is that...
Just Mg.
Mg, okay.
Yeah.
Thank you. But, but the whole stuff is defined over Mg bar. Because...
no, the infinite tower Mg bar.
Yeah, in addition to the tower.
Yes.
Okay, thank you very much.
Yes. So there's sections of content under this projective limit of varieties. But the volume only calculate on the smooth parts. You don't really care about the boundary. That's the whole point.
That's the point.
So in general, it is a stack. Do you have to take some finite covering to kill the stack? I mean, like, is it?
Oh yeah, of course. You have to do that, but it's much worse than that. You have to blow up the boundary infinitely many times.
But do you get some bundle or some power of a bundle after blowing up and after taking care of the?
No.
It's just only asymptotic in the.
Yes, I mean say the following. I give you a simple example. Think about how to define narrow heights on elliptic curve with a bad reduction, right? Each time you have a narrow model, then you make a basic change. You have another narrow model. If you want to do the regular model of elliptic curve, right? If you make a basic change, original one is regular, but the basic change is not regular anymore. So you keep adding business there, right? So this is a similar process. You keep add the data out of the boundary. Okay. My book is absolutely necessary. So I don't know how much money I can make with the Xingyi. Okay, this is the second ingredient. And I'm pretty lucky because otherwise I really don't know how to prove this thing. But I believe this is generally, this is the truth. So yesterday we discussed as one student with Xingyi, we believe we can prove this kind of thing for general varieties. But that's require tons of analysis to extend the Cordaria embedding theorem to quasi-projective variety. That needs a lot of analysis. So we're not going to do that. It's a hard analysis. The third ingredient is let me call that Gaussian. What do you call that? Criterion. Criterion and Betty rank. So I will not explain that. So this is after Gao and the master Zania. His work is complicated. I will not explain. I really don't know much about the Hodge theory. So anyway, so they prove that C1. So we use his criterion. We can prove 3G minus 3 is bigger than 0. So that's the basic consequence. Follow the same. But this is also proved. This is also independently proved. By Richard Hahn. It's a very nice story. So I know after Xingyi's work, I know after Xiang's work, someday I know the first step, second step. I really don't know how the third step. So I talked to Xiang and Richard independently, and both of them said know how to prove this stuff. So I compared the notes, right? And the Richard's proof, Han's proof exactly follows Ceresa. He works on only at the boundary. Xiang's proof exactly works on internal. He doesn't care about the boundary. So the proof actually completely complementary to each other. But I have to say, Richard's proof, Richard Hahn proof is more explicit, really tell you what's going on. So if you want to know what the U is, probably have to go back to the Richard Hahn proof, but he requires tons of Hodge theory. We have no idea how to do that. Xiang's proof, at least I can follow, right? So, and this theorem also implies some torsion, non-torsion business. The Richard Hahn gave a talk in Braun. There, after seeing the abstract, I think the Matt Kerr and Tayo gave another proof. I can say it's semi-independent because he's already seen the abstract, what the statement is. So that's basically the ingredient. Do you want to see another story about automorphic sites? I don't have time anymore. Maybe we should stop here. Thank you, guys.
Thank you very much. Questions? Comments?
Yes.
So what is the automorphic site?
I can write statement. How much I can prove? Automorphic site is the following. So we start with F totally real field. We start with quaternion algebra and ramified at exactly ramified at one Archimedean place. Let me try to say the thing. The B tensor of a Q of real number is one copy of Hamiltonian quaternions of M2 of R G minus 1. G is degree F. What?
G minus 1 goes for the first factor.
G minus the first factor. Okay, thank you. Okay, at least my collaborator correcting me. So in this way, you get a tower of Shimura curve. So it's just defined by H. Then you define it by whatever B tensor AF cross, right? And then you do this B cross there. So okay, plus the modular the U there. So you get the tower Shimura curve. So in the tower Shimura curve, then you take then of course you have XU embedding to XU the set of power, and then you embed this guy, you map this Jacobian of XU a set of power to this end, and let me see. Okay, so if you A is a quotient, suppose this guy. So this guy, suppose you have a 3 module form FGH, 3 Hilbert module form. Then you get a 3 abelian variety. Okay, you get 3 abelian varieties. So you get AF, AG, AH, 3 abelian varieties, and
you mean there are Hecke eigenforms, or the
yes.
FGH are nice, are no.
Yes, FGH 3 Hilbert eigenforms, new forms. You can do it this way. So then, okay, so you also can do a dual story. You can have a dual forms. It doesn't really matter. AH, the dual form, and then of course you have this whole thing has a map from here to there. So you get a delta FGH. You get a 3. You get a cycle inside. So you get a 1 cycle delta FGH inside AF, AG, AH. You get another cycle delta, whatever I write dual here. It doesn't really matter, because I'm not really assumed that the principally polarized. But on these 2, you have 3 Poincare bundles. One for this one, but this one for this one. So what we're going to do, you're going to, okay, actually I'm doing stupid. Okay, I have X cross X embedding to these 3 bundles. So I have this AF, F dual, AG, AG dual, AH dual. So I have a Poincare bundle here, Poincare bundle here, F, G here, Poincare bundle here. Prove by 3 bundles, I take intersection numbers, so I will get the heights. So we computed the heights, the delta FGH, FGH dual is equal to the these bundles, C1, 3 bundles, PF, C1, PG, C1, PH. So this is a better definition, automorphic word of the height Gross-Schoen cycle. The theorem the theorem is a long way. It's still not finished. In progress. So now the y is easy. Okay. Sorry. The yuan. So 2013 to 2025. Not still finished. Still okay. The modest version is that this GH, FGH, the balance block height is equal to some constant C times derivative at 2 F of GH. And the assumption, assume the other assumption that FGH has square free, have square free level at P dividing at place, dividing discriminant of B. Right. So we could not really drop all the conditions. So, but that's basic thing we can prove.
Thank you. Further questions? There are not. Thank you.